Hi, let's continue. In this topic, we are dealing with error in finite element. So the title is Interpolation Error in HK Spaces. The interpretation of CS lemma is that the error is proportional to the minimal error in approximating U in VH. To do this, we can simply choose V as the interpolation of U in CS lemma to get the error in V norm is less than a constant. Hence, CS lemma reduces the problem of estimating the error in the numerical solution to estimating error in the interpolation of the exact solution. Now let's recall the average Taylor polynomial. Since it involves only integrals of the derivatives, we can immediately use weak derivative here. So in definition 21, average Taylor polynomial with weak derivatives, let omega in Rn be a domain with diameter d that is a star shape with respect to a ball B with radius epsilon contained within omega. For f in hk plus 1, the average Taylor polynomial qf is defined as like this, where Tkf is the Taylor polynomial degree k and it involves weak derivative, evaluated using weak derivatives. This definition makes sense since the Taylor polynomial coefficients are in L1 log omega and thus their integrals over B are defined. The next step was to examine the error in the Taylor polynomial. Theorem 22, let omega in Rn be a domain with diameter d that is star-shaped with respect to a ball B with radius epsilon contained within omega. There exists a constant C Kn such that beta is within 0 to k plus 1 and all f in hk plus 1, and this statement holds. Next, corollary 23, let K1 be a triangle with diameter 1. There exists a constant C such that f minus q in hk norm is less than C in hk plus 1. The next step was the bound on the interpolation operator. Now we just have to replace CL infinity with WL infinity as derivatives may not exist at every point. Lemma 24, let K1 Pn be a finite element such that K1 is a triangle with diameter 1 and such that the nodal variables in N involves only evaluation of functions or evaluations of derivatives of degree less than or equal to 1, and Ni in WL norm is finite, and this statement holds. Let U in Hk with k greater than L plus N over 2, then the interpolation of U in Hk is bounded by C U in Hk norm. The next steps, then just follow through. Let K1 Pn be a finite element such that K1 has diameter 1 and such that the nodal variable in N involves only evaluation of functions or evaluations of derivatives of degree less than or equal to L, and P contain all polynomials of degree k and below with k greater than L plus N over 2. Let U in Hk plus 1, then for I less than or equal to k, the local interpolation operator satisfies this, the difference between interpolation and the U solution. U is bounded. Lemma 25, let K, P, N be a finite element such that K has diameter D and such that the nodal variables in N involves only evaluation of functions or evaluations of derivatives of degree less than or equal to L, and P contains all polynomials of degree K and below with K greater than L plus N over 2. Let U in HK plus 1. Then, for I less than equal to K, the local interpolation operator satisfies this. Okay, where Ck is a constant that depends on the shape of K but not the diameter. Theorem 26. Let T be a triangulation with finite elements Ki, Pi, and I such that the minimum aspect ratio R of the triangles Ki satisfies R greater than 0 and such that the nodal variables in N involve only evaluations of functions or evaluations of derivatives of degree less than or equal to L, and P contains all polynomials of degree K and below with K greater than L plus N over 2. We let U in HK plus 1. Let H be the maximum over all the triangle diameter with H from 0 to 1. V is the corresponding CR finite element space. Then for I less than or equal to K and I less than or equal to R plus 1, the global interpolation operator satisfies this boundedness. The interpolation of U minus U in HI norm is less than a constant HK plus 1 minus U in HK plus 1 space.